Okay, so next let's talk about something more specific about artificial neurons. So artificial neuron is a unit model we can use for constructing very complex deep learning models, as we will introduce later. So neuron is more like construction units, and we'll talk about what is the artificial neuron model we can use for building the deep learning models. So artificial neuron actually is more like an implementation of the natural neuron. So, given the human brains, inside our brain we have more than 100 billions of natural neurons inside it. So the human brain are composed by a group of connected neurons which are connected by the axons and the dendrites. Inside the human brain, signals are transmitted from one neuron to another via the axons and dendrites. So the connecting point between the axons and the dendrites are called synapses. So the human brain can learn something new knowledge by changing the connection strength of the synapses. So at the bottom of this page, we will provide you with an image about human brain neurons. So for the neuron, we have the neuron cell, right? It has a cell. Inside the cell, we have the cell body to be this part. And surrounding the cell body, we have many of the dendrites, which are more like branches, right? Like the tree roots, right? We have so many different branches. And these branches can actually, accept input from other neurons. They can accept the input from other neurons, and this signal can be transmitted from other neurons via the connection of these axons from other neurons with the dendrites of this neuron. They will have some connection by the ending point. So, given the inputs from other neurons transmitted to this neuron, they will connect all the inputs together. And if the input signal is strong enough, like larger than the membrane potential, if so, then this neuron will fire one spark. In other words, this neuron will be activated and also send the signal to the following neuron. And the way this neuron will send the signal to the next neuron is via this axon. This axon is more like a transmission cable, right, from the neuron cell body to the terminal bulb. So via the axon, it will transmit all the signal via the axon, this cable, to the end. And at the end of the axon, we also have some branches. These branches will be connecting to the dendrites of the following neurons instead. So you can see, right? This neuron will accept the inputs from other neurons via its dendrites, and this neuron will connect all the inputs. If the input is strong enough, it will be activated and also fire one signal to the following neuron via its axon. And the way to send this signal is via the connecting point between the axon, like the ending point of the axon, with the dendrite of other neurons. And this connecting point between the axon and the dendrites of other neurons are also called synapses. So for two neurons, if their connection points or their synapses is very strong, then this neuron will be able to send more signal to the following neuron. However, if the synapses is very weak, between this neuron and other neurons, if so, then the signal from this neuron sent to the following neurons will be much less, right? So the connection points actually will control the signals which be transmitted from one neuron to other neurons. So if you are interested in more information about the human brain neurons as well as signal transmission from among the neurons, you may refer to one of my tutorial articles about brains as shown here. This tutorial will be optional for you to read. If you have time, you can check these two tutorials to have a look at the basic architecture of the neurons as well as human brains. It can provide you with more background knowledge for you to study deep learning this area. So, based on this natural neuron, the researchers propose, do we have a way to model the natural neuron? They work. So therefore, based on this natural neuron, people propose to construct some artificial neurons which can mimic the way the neurons works. So, for the natural neuron, we have dendrites for receiving the inputs. Between them, we have the axons, right? So between them, we have the synapses, denoting their connection weights. And they will connect all the inputs. If the input is strong enough, it will fire one output to the axon to the following neurons, right? So by mimicking the way the natural neuron works, we also propose this artificial neuron as shown at the bottom. So this is the artificial neuron. This neuron, similar to the natural neuron, will also accept multiple inputs from other neurons before it. And we can denote this X1 until Xn as inputs for this artificial neuron. and we assume this neuron is connected to n neurons before it. So this x1, xn are the inputs from other neurons, and between them to quantify the connection weights between other neuron to this neuron, we denote this w1 until wn as the connection weights, right? So given the inputs and where the connection weights between this neuron and some other neurons, then we can receive all the inputs which are weighted, right, according to this input. Then we can receive the inputs from other neurons which are weighted by this w1 until wn, right? However, we need to ensure this input is strong enough for this neuron to fire an output, right? So to quantify if this input is not enough, for this neuron itself, we have one threshold denoted by the theta. This theta denoting the threshold or the minimum value for this neuron to fire one output. If the weighted summation of all the inputs is larger than the threshold, if so, then this neuron will fire one output, right? So we can quantify the inputs compared with threshold as a weighted summation by as this weighted summation by this wi times xi summation and minus theta. Theta denoting the threshold. So given all the inputs, we also need to decide the outputs, right? The way we decide the outputs is by some activation functions. We need to define some activation function. Given the inputs, what will be the outputs for the neuron? It is defined by this activation function. And finally, we can represent the outputs by this neuron as y. This y will be the output. So you can see this artificial neuron will work in a very similar way as the natural neuron. We receive multiple inputs. And for the artificial neuron, we receive input from the previous neurons, and the weight is denoted by the W here. And for the natural neuron, we'll accumulate all the inputs, and if the input is larger enough, is strong enough, we'll fire one output, right? And similar for the artificial neuron, if the input is large enough, then the threshold will fire one output. As to the output for the artificial neuron, we quantify the outputs by the activation function. So this is the basic idea of how the artificial neuron works by mimicking the natural neurons. And in the following page, we can provide you with more detailed information about one of the classic artificial neurons. It's called MP neuron. So next thing, we have multiple inputs, x1 until xn. So we can receive n inputs from other neurons. Other neuron before it, right? And the connection weight between this n neuron before it with the current neuron is quantified by w1 until wn. So we quantify the connection weights as the w as shown here. So the current neuron will accumulate all the inputs and quantify by these weights. If the input is large enough, it is larger than the threshold. If so, then we can generate some outputs, right? So for the neuron itself, it will have one inherent activation threshold of the current neuron. We denote this threshold by theta here. Then, according to the inputs as well as its threshold, we can define or we can represent the intermediate result as this weighted summation of this inputs minus the threshold. So we can sum all the inputs together and quantify by the weights, and then we also minus the threshold. And according to the intermediate result, we denote this term as z. And based on the z, we can further decide the final output by the neuron to be y equals to fx. This fx, this function will be called the activation function of this neuron. So I hope you can follow me, right? For the neuron architecture, we receive inputs from n different neurons before it, and the connection weights between them is quantified by w1 until wn. The neuron itself has one threshold. We calculate one intermediate result first as z here, and the final result and the final output by the neuron will be decided by both the z we calculate here as well as the activation function we define here. Okay, so this is the architecture for the artificial neuron we can use for building the deep learning models. And you may wonder what are the activation functions we can use to define this F mapping as shown here. In the following page, we provide you with some examples about the activation function we can use. So we can use different activation functions for the neurons. Some examples include the binary step function, the second-order function, the tangent function, the renew function, as well as soft plus function. We'll provide you, with this detailed information for this function in this page. So what is the binary step function? So for the binary step function, it is denoted by this formula. Give the inputs like x, or it can be z, right? Given the input x, then depending on the value of this x, we can assign the output as either positive 1 or 0. If the input x is larger than 0, if so, then we can generate the output to be 1. Otherwise, we can generate the output to be 0. You can see it will be like a step, right? Either 1 or 0. And then we have a jump, right? If the output is larger, if the input is larger than 0. It is very straightforward, right? For the binary step function. However, for the step function, it will have some advantage because it is very straightforward. However, it also has some disadvantages. First of all, it is not differentiable for the points like x equals to 0, right? And at this point, this function is not differentiable because there will be a jump there, right? Also, for the remaining points, its differentiation of the output versus the input will all be 0, right? In other words, it has a 0 gradient. Normally, for this kind of function, it is not very good for learning because if we are doing the learning based on gradient descent, for this function, it has no gradient at all for the remaining points. And it is not differentiable for x equals to 0 at this point, right? This function normally is not a very good choice for us when we are learning. So therefore, we have proposed another method or another function which is very similar to the step function. However, this function will be very smooth and differentiable and also have the gradient for all the inputs. One of the functions we can use is called the sigma function. We define the sigma function as seen by this formula, fx equals to 1 over 1 plus e raised to negative x. And you may wonder what is the sigma function will be like. On the right hand side, we will provide you with the curve of the sigma function, which will be the first blue line. If we draw the curve of the sigma function, we can see the function is like this. It will be, like this blue curve. For the x equals to 0, its output will be 1/2. For the x less than 0, its output will be, approaching to 0. And for the x larger than 0, its output will be approaching to 1 instead. You can see, this sigma function is more like a smooth version of the step function. For step function, we say that if the input is less than 0, it will be 0. Otherwise, it will be 1, right? We say for this function, it is not differentiable for x equals to 0 at this point. Also, the remaining gradient will all be 0, right? However, for the sigma function, it will be much smooth, right? In other words, we can ensure the gradient of the function versus input will always exist. Also, it can ensure if this x is large enough, we will approach to 1, right? Similar like this one. And for the input which is less than 0, it will approach to 0, right? Similar to this one. And we also ensure the gradient always exists for all the input values. This is for the sigma function. Another function we can use is called tangent function. We draw the curve of tangent function on this curve as well, and we'll provide the equation of the tangent function in the formula here. Fx, its tangent function will be defined as ex, e raised to x minus e raised to negative x over e raised to x plus e raised to negative x. And we'll provide the curve of the tangent function by the green curve. When we have x equals to 0, it will be equal to 0, right? And when we have x which is less than 0, it will approach to negative 1. When we have x larger than 0, it will approach to 1 instead, right? So you can see, it is also very similar to the sigma function or step function. The main difference is that it will approach to negative 1 instead of 0 as shown here, right? And for the tangent function, it will be more symmetric versus the origin point, right? If we rotate this curve with 180 degrees, it will be the same general curve. Okay, this is a tangent function. Another function we can have is called renew function. The renew function actually is also very useful, when we used them in learning. The main advantage is, For the renewal function, the main advantage is because its gradient will be larger, right? And we provide the renewal function's formula as shown at the bottom. This one, fx equals to max 0x. According to the definition, we can see that, for the input which is less than 0, its output will be 0, right? And for the input which is larger than 0, its output will be x, right? The inputs. And we'll draw the curve of renewal in this plot by the red curve. We have one flat line here, and then we have y equals to x, this line here. Right? So you can see for the renewal function, it will not be differentiable for x equals to 0 at this point, right? And for the remaining points, its gradient will be, constant. For the x less than 0, its gradient will be always 0. And for the input larger than 0, its gradient will always be a constant 1, right? Because if we have x larger than 0, fx equals to x, right? Its derivative will be equals to 1 instead. So compared with this sigma function or tangent function, the gradient for the input which is positive, its gradient will always be large, right? Which will be positive 1. So the main disadvantage for sigma function and tangent function is that it will become very flat when the x is large enough. So according to the gradient descent, for this region, its gradient will be very small, right? It will make the model, to be very difficult to learn, because if we rely on the gradient descent, and the gradient is so small because this curve is so flat, then the model learning will be more difficult. So to address this kinds of organisms, we have this renewal function, because this gradient will always be a larger number, or will be a larger value, which is constant 1. However, this kinds of renewal function, it is very good because its gradient always exists. However, the disadvantage is that it's not differentiable for some of the regions. Then we have another function which is called soft plus. Soft plus is more like a smooth function or smooth version of renewal. So for the renewal, it has some advantages. At the same time, it also has some disadvantages. One of the disadvantages is that it's not differentiable for the x surrounding x equals to 0, right? This region is not differentiable because it is so sharp. And also for the x less than 0, its gradient will always be 0, right? It's also a very bad property. So to address this problem, we also have another version which is called the soft plus of the activation function. The soft plus is more like the smooth version of the renewal. We also show the soft plus curve on the right hand side. The red line is renewal, and this lighter blue, this curve is called soft plus. You can see this one is smooth, and also it ensures when x larger than 0, its gradient is also a very large number, right? Also for the x less than 0, its gradient always exists, never be 0 anymore, right? We'll provide the soft plus as a function at the bottom. For the soft plus, we have fx equals to log. Inside, we have 1 plus e raised to x. Okay, so these are the activation function we can use for define the neurons. And you also need to differentiate the soft plus from the soft max we mentioned before, right? I hope you still remember what is soft max function we use for normalized outputs, right? Okay, so this is the activation function we can use for the neurons. So you can see this activation function plays a very important role generally. So with some of the activation function, we can ensure this model will be learnable effectively with these activation functions. You may also wonder why we have to define this activation function in this way. Why we have to define them in this way? Can we make some changes to them to define them in other ways? Why do we have to define in these strange ways? So the main reason we define this way is because if we define so, then we can compute their derivative much more effectively. And in this page, we also provide you with the derivative of these activation functions versus the input. So the activation function we define above makes it very easy for us to compute their derivative. We can show them one by one. For the binary step function, according to the previous page, we provide you with a formula to define this function right before, right? Then its derivative will be very trivial, right? So for the step function, if this x equals to 0, surrounding this origin point, its derivative will not exist, right? And for all the remaining inputs, its derivative will always be 0, right? Because we have constant output. the gradient is always 0 for them, right? And for the second function, we provide a formula here, and we can also define its derivative on the right-hand side. Given the fx, we can define its derivative to be fx, and we use this prime denoting its derivative. If you try it by yourself, you can find that its fx derivative actually equals to what? It equals to fx times 1 minus fx. In other words, given the output of this function value, we can directly calculate its current gradient by the output, right? So it is a very good property. In other words, we don't have to calculate its derivative. Just rely on this formula, we can calculate its derivative based on the output of the function directly. It is very convenient for us, right? Because we don't need to consider this function's formulas anymore. We just need to calculate its derivative by the output directly. Also for the tangent function, we showed tangent function in the previous page, and we will find its derivative fx prime equals to what? Equals to 1 minus fx squared. In other words, for the tangent function, we can also directly calculate its derivative by its output, right? It's a very good property, we will show later. And for the renewal, because it is so straightforward, we provide you with a formula for the renewal function, and we can define its formula for the derivative to be, if we have x larger than 0, its derivative will be constant 1, right? And if we have x less than 0, its derivative will be equal to 0. And if we have x equal to 0, its derivative will not exist, right? Okay, so this is a renewal. Then how about soft plus? We will provide you with the formula for soft plus showing here, and we will define its derivative to be what? To be fx prime equals to 1 over 1 plus e raised to negative x. Compared with above one, it seems this one should be more complex. However, if you further check this derivative of this function representation, you will find that this one will be what? This one will be the sigmoid function, right? You can see this, right? In other words, if we calculate the second order derivative of this function, of the soft plus function, it will be equal to this one again, right? So you can see some good properties for these functions we define here. The main reason we define in this way is because it will make it much easier for us to compute their derivatives. We can just compute the derivative directly according to the function outputs. We don't need to consider these formulas again anymore in the learning process. And in the following pages, we will show you, we can utilize these good properties with these active functions in learning.